Hey there, dear learners, and welcome back to the Lesson BCE channel. I am absolutely thrilled to have you here with us today. Real quick, if you haven't already, go ahead and hit that subscribe button and give this explainer a like to support the channel. Today, we have a truly fascinating topic lined up. We are quite literally going to unlock the secrets of time itself. We'll be looking into radioactivity, the concept of half-life, and how scientists use carbon dating to figure out exactly how old ancient artifacts really are. It's like a giant puzzle, and we're going to put the pieces together.
Okay, let's dive into this. Here's our agenda for today. First, we'll explore the mystery of carbon dating. Second, understanding half-life. Third, the decay law formula. Fourth, solving with logarithms. And finally, a real-world practice problem to test your skills.
Section 1. The mystery of carbon dating. Let's take a journey down to the atomic scale.
So, to understand how we date giant macroscopic things, like a massive wooden ship or an ancient bone, we first have to zoom way down to the microscopic atomic scale. In nuclear physics, we measure things on unbelievably tiny scales, like the femtometer. Just to put that into perspective, a femtometer is about the size of a single proton. No way, right? Which brings us to our big hook question for today. How does scientists actually know if an artifact is thousands of years old? Think about it for a second. When archaeologists dig up a piece of ancient fabric, it doesn't exactly have an expiration date stamped on the back. Moving from this historical mystery to mathematical mastery means we have to look at the behavior of the atoms hidden inside the object itself.
Section 2. Understanding half-life and unstable atomic nuclei.
The entire key to solving the age of an artifact lies in radioactive decay. So let's define this clearly. A half-life is literally the amount of time it takes for exactly half of the radioactive nuclei in a sample to decay into a stable isotope. You see, some isotopes, which are just atoms of the same element but with different numbers of neutrons, are fundamentally unstable. Now, on an individual atom-by-atom level, radioactive decay is completely random. You can't just point at one specific atom and predict when it'll decay. But when you have trillions of atoms in a sample, it suddenly becomes a highly predictable, mathematically consistent process.
And for archaeologists, there is one absolutely magical number: 5,730. That is the half-life of carbon-14, measured in years. Carbon-14 is an unstable radioactive isotope that all living things naturally absorb while they're alive. But once an organism dies, it stops taking in new carbon-14. From that moment on, the carbon it already has begins to slowly decay into a stable isotope called nitrogen-14. And it takes exactly 5,730 years for half of that original carbon-14 to just disappear.
And this beautifully illustrates the exponential decay curve of carbon-14 over time. If we start at year 0, we have 100% of our carbon-14. After one half-life, so 5,730 years later, we're down to 50%. Let another 5,730 years pass, and it halves again, dropping down to 25%. It's not a straight line, it's a non-linear, exponential decrease. It creates this beautifully smooth curve, showing exactly how carbon decays completely predictably over millennia.
Section 3. The decay law formula. How we actually model this decay over time. Now, what's really interesting about this is that we can take this complex exponential relationship and structure it logically to find exact answers. We can't just eyeball a graph, right? We need a precise equation to solve for the exact age of an object. This is the carbon-14 decay formula. The main equation models the remaining amount of carbon based on time, but through the magic of algebra, we can rearrange it to solve directly for t, the time elapsed.
Let's decrypt these variables really quickly so the algebra doesn't feel intimidating. A is simply the remaining amount of carbon-14 that we measure in the artifact today. A sub 0 is the initial amount of carbon-14 the object started with when it died. T is our target, the time elapsed in years. And 5730 is for sure our half-life. By mapping these letters directly to the real-world properties of our artifact, the math becomes super tangible.
But since radioactive decay is an exponential function, we run into a slightly tricky mathematical problem. How do we mathematically undo an exponent to isolate our time variable? Well, the answer is logarithms. Logarithms act as the mathematical undo button for exponential decay. Because exponential decay happens in multiples, we have to use logarithmic functions as the inverse operation to solve for the exact time. It's pretty brilliant. Section 4. Solving with logarithms. A step-by-step application.
Let's put this into practice step by step so you can see exactly how archaeologists calculate an artifact's age in the field. Here is a clear scaffolding of the math operations to build your confidence up. Step 1, set up the ratio of the remaining carbon, so that's our A, divided by A sub 0. Step 2, apply the rearranged logarithmic formula using that ratio. And step 3, calculate the exact years elapsed. Let's try one out together, shall we?
Here's a guided example for us. A wooden tool is unearthed, and it contains exactly 25% of its original carbon-14. Determine its approximate age. Think about our steps. The remaining ratio is 25%, which is 0.25. How do we plug that into our logarithmic undo button?
So the crucial point is right here in the calculation. We take our time t, set it equal to negative 5,730, and multiply that by the log base 2 of our ratio, which is 0.25. When you punch that into a calculator, the logarithm perfectly undoes the exponent, and boom, it gives us an exact answer of 11,460 years.
Let's move to a logic check and see how this builds just to make sure our math is solid. One half-life leaves us with 50% remaining, taking 5,730 years. Two half-lives mean the 50% halves again, right down to 25% remaining. And what is 5,730 multiplied by 2? It's exactly 11,460 years. The logarithmic formula completely backs up our logical progression of exponential decay. It hits the nail on the head every single time.
Section 5. Real-world practice problem. Time to test your mastery.
All right, now it's your turn. We've seen how the math and the physics play together perfectly. Here are the parameters for your exit ticket. An ancient bone fragment is discovered by a team of researchers. They test it in the lab and find that only 12.5% of its original carbon-14 remains. Your task is to calculate its approximate age using the exact decay formula we just walked through.
And hey, here is a quick hint to get you started. 12.5% remaining means your ratio of A over A sub 0 is exactly 0.125. I want you to work through the formula yourself and then drop your final answer in years down in the comments below this explainer. I can't wait to see who gets it right.
Actually, before we wrap up, I want to highlight one absolutely critical concept from our sources today. Carbon-14 dating becomes significantly less accurate for materials older than 50,000 years. You might be wondering, why is that? Well, because after about 9 half-lives, the remaining carbon levels become exponentially tiny, so incredibly microscopic that they are extremely difficult to measure accurately. So there is a hard physical limit to this specific dating method.
Which leaves us with a truly fascinating, provocative thought to end on. If carbon-14 dating maxes out at roughly 50,000 years, what isotopes do scientists use to date dinosaur fossils that are literally millions of years old? I'll leave you to ponder that one. Thank you so much for hanging out with me today for this explainer. Keep exploring, keep questioning, and definitely don't forget to like and subscribe for more Lesson BC explainers. See y'all next time.